Hello friends, welcome to new lessons. Again we meet here with a new topic of thermodynamics, that is about the steady flow and mass and energy analysis of the control volumes. So this is a very important topic. It has its applications in case of condenser, diffusers. Whenever the mass rate flow through a turbine or through a pipe, you can say changes how it is managed. In this case, the mass and energy analysis of a closed volume. So the first basis of this is the conservation of energy for this control volume. The conservation of mass and the conservation of energy principle for the open system or the control volume applies to the system having mass crossing the system boundary or the control surface. In addition to that, heat transfer and work crossing the system boundaries, mass carries the energy with all its crosses the system boundaries. So you can say the mass and energy content of the open system may change when mass enters or leaves the control volume. So basically we'll discuss about what are the analysis when mass changes but the the volume is remain controlled, that is it is remain constant. Thermodynamic processes involving control volumes can be considered in two groups, that is the steady flow processes and the unsteady flow processes. During a steady flow process, the fluid flows through the control volume steadily and experiences no change with the time at a fixed position. You can see in this diagram the mass V1 and the mass M1 and volume V1 is entering through this inlet, and this is the control surface where the volume is VCM, and the outlet, through this outlet mass of ME and volume of VE is ejected. The inlets and outlets are kept at different heights Z1 and ZE. So we'll study what happens in these types of cases. So let's review our concepts of mass rate flow or mass flow rate and energy transport by the mass. Once you study the development of this general conservation of mass presented in the text, here we present an overview of the concepts of important to successful problem solving techniques. First is the mass flow rate, that is mass flow through a cross-sectional area per unit time is called the mass flow rate. It is denoted as m dot. Note that this dot over the mass symbols indicates that time rate of change, that is this mass changes with time. It is expressed as m dot equals to line area integration of PV rho V into dA. Mass is given as rho into Vn as at a particular area into dA, where Vn is the velocity normal to the cross-sectional flow or area. So this is the actual flow, but we consider, you can see this bulking outside, this is the actual flow of mass when it travels from one point to another in a cylindrical pipe like structure, but at an average we consider it as like this. Now if the fluid density and velocity are constant over the flow of cross-sectional area, then the mass flow rate, that is m dot, will be rho V, this is the velocity, V average into A, that is V average into A by V, where rho is the density and this density can be represented as equals to 1 by V, and A is the area of cross-sectional. Don't be confused with this volume, this is a specific volume, it is just the reciprocal of this density. Now with these two formula, it is better to analyze them with doing the numericals, and previous videos we have discussed about the pure states, and in that we have read about the quality factors and several other things, so it has a small application in this part also. So the example is like this: the refrigerant 134A is at 200 kilopascal, the quality is 40%, that is a dryness quality, X is given as 40%. It flows through a 1.1 cm inside diameter D with a velocity of 50 meter per second. Find the mass flow rate of the refrigerant. Now in this case P is given, X is given, so we need to determine the specific volume. Now just go back to the previous video about the pure states, pure substances, the properties of pure substances. In that, how you are calculating from a given pressure value the specific volume. So we need the steam table, and after considering the steam table we get the total net specific volume V is equals to Vf plus X into Vfg. This Vfg is similar to Vf minus Vg. So from the steam table we get the values of Vf, Vfg, etc. and X is given as 0.4. So the net specific volume is 0.04. Now after getting this specific volume, the reciprocal of this specific volume will give us the density. So we'll consider the mass flow rate as V average into A by V, that is the specific volume. This average, this area can be written as pi d square by 4. Similarly, by substituting all the values, we get mass flow rate m dot is equals to 0.117 kg per second. So this means the mass of flow 0.011 kg is flowing per second through the pipeline or anything you are considering. In this case, we have considered a small tube-like structure. So in this way, we can work out with small numericals. The fluid volume flowing through a cross section per unit area is called the volume flow rate V. The volume flow rate is given by integrating the product of the velocity normal to that of the flow area and the differential flow area over the flow area. That means V dot is equals to V into A. The mass and volume flow rate are related as in this way, m dot equals to rho into V dot. So this V dot we can substitute this rho as specific volume, the reciprocal V dot by specific volume. So one more simple example. Air is at 100 kilopascal, 500 degrees centigrade, flows through a pipe with volume flow rate of 40 meter cube per minute. Now we calculate the mass flow rate. So assuming the gas to be ideal, we have V equals to PV equals nRT, the ideal gas equation. So V, that is the specific volume, equals to RT by P. We get the specific volume 0.9. Now for this mass from the volume equation, that is previously we have learned about if area is given, then how to calculate the mass flow rate. If volume is given, how to calculate this volume by the specific volume. So 40 meter cube by the specific volume which we got in the previous case. Always convert in seconds. This is in minute, convert into seconds. So we get 0.7 kg per second. So this has given you clear idea about how to calculate or work out with these mass flow rate equations. Now the conservation of mass for general control volume. The conservation of mass principle for the open system of control volume is expressed as sum of rate of mass flowing into the control volume minus sum of rate of mass flowing from control volume. Remember this last terms, into the control volume and from the control volume. That is equals to time rate change of the mass inside the control volume. So m inside minus m outside, that is into and from outside equals to m system. Now talk about the steady state or the steady flow processes. Most energy conservation devices operate steadily over long periods of time. The rate of heat transfer and work crossing the control surface are constant with time. Under those conditions, the mass and energy content of the control volume are constant with time. Please be patient because I have written this text because even if you are not quite clear of my voice, so you can get the idea from the text. So I have kept it in front of you in the slides. I don't want to make this messy, but you should get the concept clearly. Now the steady flow or steady state steady flow conservation of mass can be given as, since the mass of the control volume is constant with time during the steady state or steady flow process, the conservation of mass principle becomes sum of rate of mass flowing in the control volume minus sum of rate of mass flowing from the control volume. So summation of all the masses going inside equals to summation of masses going outside. It is given as kg per second. Now there are special cases like steady flow of an incompressible fluid. Now in this case the mass flow rate is related to the volume flow rate and the fluid density by m dot is equals to rho into V dot. For one entrance, one exit one exit steady flow control volume, the mass flow rates are related by. Now we'll consider the steady flow cases, that is the mass entering into it and going outside is equal, m in equals to m out. Substituting into rho and volume terms, we get like this. And this, if the rho density, rho in equals to rho out, that means it is incompressible. As we have considered this is a special case, the fluid is incompressible. So what we get is V in equals to V dot in equals to V dot out, that is the rate of change of volume into going into through the tube or coming out of the tube. This V dot can be further written as V, velocity into area of input and output respectively. Now you need to take precaution about something like this result applies only in case of incompressible fluids. Never use it in case of compressible fluids. Most thermodynamic systems, ideal processes involving compressible fluids such as ideal gases, steam, and the refrigerants do not apply to these relations. So now again one numerical. Incompressible liquid flow through the pipe shown in the figure. You can see the figure. Incompressible liquid is flowing. So whenever you come across this term like incompressible, you have to use the above relationships. Now in this case the diameter changes from 2d to d. So we'll solve it in this way. Initial mass m dot equals to p del v. Similarly, we get by the previous relation we get v1 dot equals to v2 dot, and after substituting all the terms, we get v2 equals to 4 times of v1. That means the option D was 4 times of v1. So I think these problems are quite simple, and these are building your basis, all your concepts very clear. Now let's talk about the flow work of energy of a flowing fluid. Energy flows into and from the control volume with the mass. The energy required to push the mass into and outside the control volume is known as the work flow or the flow energy. The fluid upstream of the control surface acts as a piston to push a unit of mass into or outside the control volume. Now if you consider the unit of mass entering the control volume shown like this, in this case this is an imaginary piston. The volume of the initial side is V, pressure P, and mass M. Now the piston will move through a distance of L, and inside it is a control volume, and with this piston will move outwards. So what is the work done in this case? So as the fluid upstream pushes the mass across the control volume, the work is done on that unit of the mass in this part. So W flow will be FL, or you can say it is FL into A by A, or PMV, pressure into mass into volume. So W flow is equals to W flow by M, specific flow or W flow per unit mass will be given as P into V. Now this term PV is called the flow work done. You should remember this. PV is called the flow work done on the unit of mass, per unit mass. Now the next thing is the total energy of the flowing fluid. The total energy of a flowing fluid by unit mass as it crosses the control surface is the sum of the internal energy. You should remember these things. A sum of the internal energy, flow work, and potential energy and kinetic energy. So this work done, or you can say the total energy of the flowing fluid given as theta is equal to summation of all the 4 types of energy like internal energy U, flow work PV, kinetic energy V square by 2, and potential energy Gz. So here you have used the definition of enthalpy, which we learned in first law of thermodynamics, H equals to U plus PV. So these formulas are quite simple. You just need to remember the concept corresponding to these formulas. Now the energy transport by the mass. Amount of energy transport across a control surface is E mass equals to m into theta. Theta is the total energy of the flowing fluid. So m into H plus V square by 2 plus Gz. Now rate of energy transport across a control surface is given as m dot. If you consider E dot mass equals to, that means it is changing with time, rate of change of energy. So equals to m dot rate of change of mass into work done is equals to m dot h plus v square by 2 plus dz. Now the conservation of energy for general control volume. The conservation principle for the control volume open system has same word definition as the first law. That means the rate of net energy transfer by heat, work and mass is equals to the rate of change in internal energy, kinetic energy, potential energy, etc., or any some other kind of energy. That is E in minus E out equals to del E of the system. We consider that the energy flows into and from the control volume with the mass. Energy enters because the net heat is transferred to the control volume, and the energy leaves because the control volume does net work on the surrounding. So the open system or the control volume, the first law becomes Q equals to summation of all the masses inlet minus W net minus summation of all the masses outlet, which is equals to net change in energy per time. Now in this case you consider where theta is the energy per unit mass flowing into and from the control volume. The energy per unit mass theta flowing across the control surface that defines the control volume is composed of four terms, that is the internal energy, kinetic energy, potential energy and the flow rate. So this we have learned previously. Theta is equals to u plus pv plus v square by 2 plus dz. Now if we consider for both the inlet and outlet, simply we will write in this manner: Q net, that is from the inlet side, plus for the inlet total work done m into h plus v square by 2 plus dz, minus some work done in the movement minus at the outlet, and that is equals to net change in energy, where the time rate of change of energy of the control volume has been written as del ECV. So this is a very important formula and quite easy to remember. So you must be clear how we have written this formula in case of the steady flow of the fluid. The most energy conversion devices operate steadily over long periods of time. The rate of heat transfer and work crossing the control volume are constant with time. So in this case, these conditions, the mass and energy content of the control volume are constant with time, like dmcv by dt equals to del mc, and dEcv by dt is equal to del ECV. So steady state, steady flow conservation of mass is the summation of all the masses going inside equals to summation of all the masses going outside. Since the energy of the control volume is constant with time during the steady state flow, the conservation of energy principle becomes, as in this case you can consider, the sum of rate of energy flowing into the control volume is equals to sum of the rate of energy flowing outside the control volume. You just need to be clear about this concept. In case of considering conservation of mass, the input side and output side has to be equal, and so we come up with the same formula: Q plus W plus inlet plus equals to Q out plus W out equals to outlet, the work done at the outlet state. Now if there is an steady flow for one entrance and one exit. Now I was talking about some thermodynamic devices like pumps, compressor, turbines, nozzle, diffusers, which they have one entrance and one exit. So the steady flow, steady rate conservation of mass, the first law of this reduces to m1 dot equals to m2 dot, and you can substitute it. You are quite comfortable with these formulas now, I guess. So this is, don't be afraid of this so many numerical terms. There is a in the last slide you can see this is the final formula, and for easy application the final formula has been constructed, means if they have been transferred to a particular unit or standard units, in case of kilojoule per kg, 1000 meter square second square, in this way. So you need not to worry about this. These are just numericals, nothing else. When the kinetic and potential energy can be neglected, the conservation of energy equations will become in this form, like Q, net change in Q and work done, Q minus W is equals to M into H2 minus H1. And if you consider for unit mass flow, then it will be small q minus W equals to H2 minus H1. Now here is the pictorial view of some of the engineering thermodynamic devices. This is a nozzle. You can see just the reciprocal is a divisor. There are some more devices like turbine, chambers, throttling devices, compressors, heat exchangers, and so on. So coming to the first type of thermodynamic device, that is a nozzle and the diffusers. In this case, volume V1, and in the outlet it is volume V2. Sorry, it is the velocity V1 and V2. Now as you can see at the next part, at the outside outlet part, the velocity will be large because the area of cross section decrease, so V2 is greater than V1. Similarly, in case of diffuser, the V2 is less than V1 because the area of cross section is increased. For flow through these nozzles, the heat transfer, work and potential energy are normal neglected, and the nozzles have one entrance and one exit, so the conservation energy becomes now we actually come to the application part of what we have read previously about the steady flow of energy and mass. So M input equals to M output, M1 dot M2 dot equals to M dot. So if we write the whole equation in this form, Q plus work done equals to W net plus net work done, we'll get this formula, M into H1 plus V1 square by 2 equals to M into H2 plus V2 square by 2. So for solving, the velocity V2 will be is equals to 2 H1 minus H2 plus V1 square. Now there is an example for your clear knowledge. Let me show you this example. A steam at 0.4 megapascal, 300 degrees centigrade enters an adiabatic nozzle with a low velocity, leaves at 0.2 megapascal, quality 90% means X. So again, bring all your knowledges and all your numerical quantities, like you need to consider everything in this problem. So the control volume is the nozzle, property relation you will get from the steam table, and the process is adiabatic or steady flow. So by considering the conservation of mass and conservation of energy, we get both of this formula, and neglecting the inlet kinetic energy, the exit velocity will be V2 equals to 2 into H1 minus H2, and H1 and H2 you will get from the steam table, because at corresponding steam table, that is, it is given as T1 equals 300 degree and Pascal pressure 0.4 megapascal, so it comes up to its superheated state, and you will get the corresponding H values from the steam table. And after substituting all the values, you will get H2 equals to HF plus X2 Fg. Putting this value of H2 in case of V2, we will get the value of net outlet velocity. Similar as the turbine case, same, mass is going inside, mass is coming outside, there is a control volume surface in the middle, and the formulas are still the same. Now there is one more question, you can go through this question. Now the control volume is the turbine, process is steady state, assume the ideal gas equations, ideal gas relations. Similarly, we apply this formula, energy, conservation of energy, and substituting the values from the steam table. Just combine all your knowledge about the steam table and this chapter, and you will get all those answers. So you can go through these numericals, these are quite easy and will build your concept more strong. So in the next video we will discuss about the throttling devices and many other thermodynamic devices in the next video. Thank you.